I'd like to introduce our presenter for today, Aaron Dirk, who's a product leader at Immubit. Aaron will take it from here.
Thanks, Allison. Like Allison said, I'm a product leader here at Immubit. I have over 10 years of experience in the refining industries. I was fortunate enough to be one of the first employees at Immubit, so I have now almost 6 years of experience building AI models. I've gotten the opportunity to see the technology from a lot of different lenses. With respect to Immubit in general, we have over 70 closed loop applications running today. 7 of the largest 10 US refiners use Immubit to help optimize their most complex strategies. And we typically see between 10 and 20% improvement in energy efficiencies and 30 to 50 cent increase per barrel increase in margin. Before we get into the webinar itself, we just want to learn a little bit more about you. We have 2 really quick polls for you. So if you see on the bottom right of your screen, there's a little icon that says polls. If you select that, we can just go through it really quickly. The first one is, and I think they're published already, Allison. The first one is, where are you currently on your AI journey? I'll give you a couple moments to answer that question. And then the second poll is, I think Allison will publish it here shortly. Yep. Where are you currently in your AI journey? I'll give you another couple moments to fill that out. So it looks like a lot of people are saying that we know we need AI and we want to explore solutions. Some people are saying that they're at the beginning, looking to learn more. And we have sounds like one more advanced audience member saying that they've already implemented some AI-based optimization, which is great. Okay, thank you all very much for the responses. We will dive straight into the presentation now. So today we're going to talk about hybrid models versus true AI models, and what are some of the best practices to maximize value and minimize emissions. From the highest level possible, this is what our technology does. It reads the current conditions of a plant. It also incorporates information from the user, whether it be prices or constraints or various other things. And then we have an AI model that makes decisions and optimizes on a minute-by-minute basis. It's important to note that optimization in this sense is a general term. It can mean economic optimization, environmental optimization, or maybe just operational goals. Before we get into our particular technology, which is called deep learning process control, I want to talk more about the actual problem statement in general, and then the potential of AI to help solve this problem. And then obviously we'll get into our technology. So what problem are we trying to solve? And the answer is there are a handful of complex decisions in each plant, maybe 5 to 15, that are very valuable. As an industry, we've spent a lot of time and effort trying to improve these decisions over decades, and we've done a lot. We've captured a lot of this value. There's still value on the table. Some of the things we've done is we create kinetic models. A lot of times these kinetic models are based on pilot plants. We build actual pilot plants to build these models to help us make better decisions, among other things. We build rigorous steady state models where a domain expert spends a lot of time trying to model the process to understand more about it. We've developed advanced process control. And a little bit more recently, we've linked a lot of these technologies together to try to help solve these problems. So let's talk about all those different technologies and how they kind of fit in solving this problem, these most complex optimization strategies. On the left, you can see an example of this. This is just a theoretical textbook example of a hydrocracker reaction. And you can see it's complex in that teal curve there, the diesel yield curve. So you can see at the left part of the chart, as you increase conversion, you actually make more diesel. But then on the right part of the chart, as you increase conversion more, you start to overcrack and you actually make less diesel. This is a very complex thing to model. We've tried very hard and done a lot of great things. And it's something that we still struggle with sometimes. There's still value left on the table when modeling this and optimizing in real time. So let's talk about kinetic models. So these use standard equations and data from a pilot plant. And then you take that information and bring it to your plant. So some of the sources of error are that you can't test all the different combinations. The pilot plant is different size equipment from your actual plant. There's the feed composition that can change. There's the different conversions, the different catalyst degradations. All these combinations of these different aspects can't be tested. And so at the end of the day, you have to extrapolate some onto your plant. So there's some sources of error there. A lot of, not all, but a lot of best-in-class LPs utilize this type of information. We also have first principle simulations. These use a bit more generic equations, and they have a domain expert make dozens, or I think in reality, it's more likely hundreds or thousands of specifications. Some of these specifications we know. For example, we know the reactor dimensions. Some of the specifications we don't know, and we have to kind of make some assumptions. We don't know how much the catalyst has degraded at any point in time. We don't know the feed composition typically, so we have to make some assumptions there. Let me go back. The first principle simulator, this is what a lot of real-time optimization technologies are based on today. We also have step testing, which is what advanced process control is typically based on. This is great because you make changes to the actual plant and record those changes. So it's based on the actual plant, but it only produces a single gain, typically a single relationship. Sometimes you can do a bit more, but what you wouldn't get is a robust understanding of this ever-changing relationship. These traditional technologies matured and plateaued decades ago. So let me kind of expand on what I mean by that. This is kind of just a traditional technology S-curve. Most technologies, I think, experience this type of curve. At first, there's slow evolution, and then there's some breakthroughs that enable rapid improvement. And then there's plateaus due to scientific limitations. The breakthroughs and corresponding plateaus for these traditional technologies happened in the 80s, 90s, and 2000s for the most part. So what scientific limitations cause these plateaus? The short answer is assumptions. The longer answer is too many hard assumptions that deviate too far from reality. So in this abstraction, we have reality, and you can see sometimes you can make assumptions, and in this case, it models reality pretty well. This might represent a lot of things that you use these technologies for today. And in a way, it's what a lot of these technologies were meant to do. They do a great job at it. Some more simple control mechanisms, or maybe like sizing equipment, things like that. As the problem increases in complexity, you need more and more of these assumptions, and they deviate further and further from reality. I'm going to come back to this point a couple times in the presentation. For closed loop optimization of complex strategies, I'm not talking about for all the other things that these technologies have really done an amazing job at. For optimizing your most complex strategies in closed loop, this many hard assumptions can sometimes render models ineffective. So let's talk about these assumptions. The point I'm trying to make here in this slide is that not all assumptions are created equal. We have assumption error there, and it's increasing as you go to the right. And so something that we're very confident with as an industry as a whole is mass balance. It's rooted in the underlying rules of physics. It's well accepted. There's not that many things that affect it and cause any deviations. There are some things, so it's not perfect. It's not perfectly without assumptions. We don't typically measure mass. We typically measure volume. So converting to volume to mass, there can be some issues. There's some units that actually have volume swell or volume loss. Anyways, generally, this is a first principles concept that we're very comfortable with. It doesn't have very much assumption error. There's also distillation. Again, we're pretty comfortable with this as an industry. There are things like tray efficiency. It's literally a fudge factor because we can't always model things perfectly. Also, there's flooding regimes that aren't modeled well by traditional equations and first principle concepts. But again, generally, we're pretty comfortable with distillation as an industry. As we move further to the right, we have a vapor-liquid equilibrium. I like to talk about this one because it's kind of hidden in your first principle simulation, right? You have to choose an equation of state. It's not always obvious. There's no absolutely right answer whether I choose Peng-Robinson or SRK. And that one specification carries a lot of assumptions with it. On top of that, typically we don't know the feed composition, at least in a lot of plants and refining especially. So we have hypothetical components that are not even based on real molecules. You're starting to see, I think, there's a lot more assumptions built into these types of things. Lastly, I'm highlighting reactor kinetics. These are typically associated with some of those most complex decisions that are very valuable. And I want to make the point again, these kinetic models are super valuable. They've added so much value to the industry and continue to do so. But especially in closed loop optimization, you're introducing a lot of assumptions, particularly extrapolating this pilot plant inflow information onto your plant. One of the concepts I'm trying to point out here is that when you have assumptions that you're pretty confident in, that you think are going to be pretty close to reality, we want to incorporate all of this information. This domain expertise is important to incorporate in our models. And when you are confident in those assumptions, we can be a bit more direct and definitive. When you're less confident in the assumptions, and when you know that it's not going to match reality perfectly, we want to be a bit more subtle and a bit more targeted in how we introduce these concepts. Okay, now let's talk about the potential of AI to solve these problems. So the answer to these critical decisions actually exists within your data. Inside your historian, you have a lot of information about what's happened in history, all of these nonlinearities and complexities and time dynamics and disturbances that are happening that have traditionally made these decisions so hard to make. The answer actually exists within your data, and AI now unlocks this value potential. Your data is much more valuable today than it was 10 years ago. But if we incorporate all these assumptions, and if they start to deviate farther and farther from reality, you start to destroy and erode the value potential of the data and really of AI itself. By design, traditional technologies require so many assumptions that are then imposed on AI models and can really, like I said, degrade the value of these models. I'll give a small example. Say you have an AI model, just a small AI model for, let's use the tray efficiency example. Use your AI model, and you don't impose anything on that AI model at first. You don't impose any of the McCabe-Thiele equations. You don't impose any of the equations of state. You just use AI and help predict this quality. Then you go and put that into a first principles model or a traditional technology, and now those assumptions are implied onto the overall model, and it's going to mismatch from your AI. It's going to erode the value that you maybe could have captured from the data itself. So I'm talking kind of about how AI is the answer, and I think you're probably hearing a lot about this generally. And I think the obvious question is, okay, how can AI work if my data is flawed? I know my data is flawed, and that's completely correct. In every project we've had flawed data, and we've had to deal with it. And we deal with it in a variety of ways. The first is that we have domain expertise, domain experts between ourselves and our customers clean, analyze, and transform the data. We don't want to include data that's not representative, probably during shutdown and startup. We don't want to include that. Maybe we can transform the data, take maybe a ratio instead of a flow rate, things like that, to really help get the data in the most pristine state possible, which still is not perfect. Another thing is that AI has a property of learning across an entire data set and consolidating learnings, similar to how a human does. So for example, if there's one piece of data that's flawed in a certain way, it doesn't mean it's useless. It can still learn something. Maybe it can't learn everything. And then there's a different piece of data that's flawed in a different way. Again, it can still learn something. And then it can piece those two pieces of learnings together. Here's a quick example. I'll give you a couple seconds to see if you can read this. So most people can read this. And it really is cool how the brain can piece together different pieces of information. You don't actually need perfect data. You have enough experience over the years reading and processing text and conversational information that you can piece it together versus based on all of the different learnings that you've experienced in your life. AI can do something similar, and it mitigates the risk of flawed data. Again, it doesn't solve it completely. This isn't enough. AI models need to be guided with first principles to correct for bad data. We have a ton of domain expertise in this industry, and I'm sure in this room. And we want to use that to help guide the models in the right direction. So here's another abstraction. You can see on the y-axis, on the vertical axis, you have model accuracy. This isn't a specific definition, though. You can think of this as even model usefulness or utility. And then on the x-axis, the horizontal axis, we have first principles confinement. So this is how much you've confined your model to first principles concepts. Again, I'm making this point for something relatively simple like controlling a binary distillation column. That optimal point can be much further on the right, where you can constrain your model very much to first principles and still do a great job. But again, we're talking about closed loop optimization of your most complex strategies. And in this case, there exists an optimal. You can see as you go from left to right, as you increase first principles confinement, as you confine the model to some first principles concepts, you guide AI, and this actually increases model accuracy or model utility. But there reaches a point where you start to introduce too many assumptions. It disagrees with the data, with reality, and it devalues the data, and eventually it decreases the accuracy and the utility of your model. So you want to find that optimal point. So let's think about how this compares to traditional technologies. So obviously, traditional technologies are much further on the right, first principles simulations being the extreme example where they're literally based on first principles. And I also want to point out, this is just an abstraction. This is not based on data. This is just our opinion at any bit here. But the relationship isn't even linear. There reaches a certain point where you've introduced so many assumptions that are going to disagree with the data so far that you lose the potential of AI. And this is kind of how we see it. There exists on the left true AI models. And within that space, you still want to find that optimum, right? You need some first principles concepts. You don't want to go too far. And that's part of the model building process, that you want to find that optimal. And then with more traditional technologies starting from the right, you have your first principles or table-based models. And you can introduce AI to those. You can build some hybrid models, but at the end of the day, if you're plugging those hybrid models back into first principles simulations, you haven't escaped the problem of the assumptions, and you're not going to be able to get over that hump and achieve the true value of AI. So it's kind of more about industry and AI and traditional technologies in general. I'll dive in now to our specific technology. So our technology is called deep learning process control. It's made up of two main parts. And this is actually similar to a lot of other technologies. There's that the two parts exist. The first part is a nonlinear process simulator. So this is an AI model that takes years of data from your historian and essentially uses that data to predict the dependent variables in the future. It's predicted on a dynamic basis, so it's not just on a steady state basis, and with nonlinearities. There's not just a single gain or relationship. There's all of the complexities and nonlinearities are understood by this model. Then, and this is done with AI models. It's called supervised learning, which is one of the most common forms of AI. Then, once we have this nonlinear process simulator, we use that simulator to run a lot, millions and hundreds of millions of trial and error scenarios. And we create a model using reinforcement learning. And this is a truly cutting edge type of AI. And it results in a controller with an experience-based optimization strategy that can understand what's happening in real time. It's important to note that all of this is done offline and in the cloud in a safe environment. This This is where the need for supercomputers occurs. Once we have a model that we're happy with and that our customer is very comfortable with, then we bring it on site and put it in closed loop. At this point, you no longer need a supercomputer. It will always converge within a matter of seconds, and it can do so on top of your existing hardware. There's one additional part of our technology, and it's the reason I didn't include it at first is because it's not a core piece. We're calling it statistical analyzers here. You probably know them as inferentials. So whenever someone takes a lab, we need it, and you only take it infrequently, maybe a couple times a day. We need continuous information for that property if it's important to control to. And so just like in traditional technologies, we create inferentials. This is not a core part of our business because it's not a high data regime. It's a low data regime. Depending on how frequently you take lab samples, you either have hundreds or maybe thousands of data points. And this is just not enough data for AI to really do better than traditional technologies. We start with neural network inferentials, AI inferentials. They're typically better, but not always, and not by that much. So sometimes we use just regular linear regression like most people do. Sometimes we use AI for it. It's important to us because it's important to solve the problem, but again, it's not a core part of the technology. The core parts are this one process simulator and this controller and optimizer. And it's similar, most control technologies have those two pieces. Like for example, advanced process control, for this prediction piece, they have step testing. They build a model based on step testing. And then there's a solver here. Or like for a lot of real-time optimization technologies, this is a first principles model to make the predictions. And then another, again, a solver here. So it's similar in the architecture, but the key difference is that both of these are AI, particularly this piece is really cutting edge for type of AI. So I'll dive into those two pieces. The first piece, the nonlinear simulator that I was calling it previously, we call that a deep learning predictor, or DLP. So what we do is we take years of data from the historian and we turn that into hundreds of thousands of process states. A process state is essentially what a person would look at to make decisions in the near term. It's more or less the time to steady state of the process. So we take these hundreds of thousands of process states in their dynamic sense, in their true resolution, not averaged out. And we say, okay, model, here's all the independent variables, try to predict the future of the dependent variables. And you can see here in the first situation, it might not be that good. There's a lot of error, and you can even see that the prediction is going in the wrong direction. And then over hundreds of thousands of these cases, the model learns to predict the dependent variables well in their true dynamics and in their true nonlinearities. We actually iterate through dozens of model versions when we do this, and we have domain experts and our customers do a lot of analysis to make sure that we agree with what the model has learned. This is where a lot of the first principles and domain expertise is incorporated in models. You can see on the right there, it's some of our visualizations that we have. On the top right, you have your time to steady state plot. This is saying for this particular relationship, and we do this for all relationships, there's about 4 steps of dead time where the dependent variable didn't really react. And then there's an additional 5 or 6 steps of transient time, and then it reaches time to steady state. And if you look at the bottom right, this is one of our most important visualizations. We call this a gain distribution. It represents the relationship between 2 variables, and we'll dive into that. We'll dive deeper into that one here. So this is just a simplified hydrocracker flow diagram. If you look at the bubbles, the bubble on the top left, it represents a relationship between feed rate and diesel product rate. And you can see that this is pretty linear, right? And it makes sense. As you increase total feed, you're going to get more diesel. A linear model maybe would do a good job modeling this. And then let's look at the other 2 bubbles together, right? This is reactor conversion. We have it here as weighted average bed temperature. And you can see as weighted average bed temperature changes, it's unclear what happens to diesel product flow. This actually agrees with what we would expect from a domain expertise perspective. It's that same chart that I showed before. This is a very complex reaction and valuable. It's very valuable to get this decision right And it's hard to know exactly where you are in that curve. And by the way, this is an oversimplification. That curve is constantly changing as the catalyst degrades, as the feed composition changes. So this is a big challenge. You can see here, this is exactly what the model learned. So this is a representation of all the different relationships that the model learned. So for example, on the right, you can see this is the undercracking regime, where if you increase conversion, you're going to actually increase diesel product rate. And on the red part, this is actually where you're in the overcracking regime, where as you increase conversion, you're going to actually decrease diesel yield. So you can see the model didn't just learn one relationship or two relationships. The model learned the full distribution of everything that was seen in history. And then that whole visualization is shown again on an interactive application. The users here can look at the relationships between any of the variables, dive into the data. It's a very interactive application where you can filter and you can say, oh, okay, let me investigate the times where this is a positive relationship. Highlight that, and everything else will interactively update, and you can kind of deep dive into it. A lot of our customers are liking this functionality, not just to understand the models, but to understand their own process better as well. Okay, so that was the first piece, the prediction piece. We call it the deep learning predictor. Now let's talk about the second piece, the deep learning controller. So again, this is trained based on a cutting edge type of AI called reinforcement learning. And what I'm trying to cover here is something we call the reward function. So as you train a reinforcement learning algorithm, it essentially goes through a lot of trial and error scenarios, just like how we learn as humans. In this case, it goes through hundreds of millions of trial and error scenarios. And at the end of each one, we have to tell it whether it did a good job or whether it did a bad job. And this is how we tell it that. So you can see there's kind of three tiers. The first tier is the manipulated variable bounds. So we tell the model, I don't care how good you did at everything else. I don't care if you respected the controlled variable bounds, and if you increased the objective function by a lot, I don't care. If you violated manipulated variable bounds, you did a bad job. Then that next tier says, okay, as long as you're within your manipulated variable bounds, now I don't care how much you increase the objective function, as long if you violated your controlled variable bounds, you still did a bad job. And then finally, in the last tier, we tell the model, okay, as long as you're respecting your manipulated variable bounds and you're respecting your controlled variable bounds, now we're going to grade you on how well you optimize the objective function. And it results in a model that simultaneously respects all the constraints while optimizing. This is how it actually works. So you have your DLC here. This is during training, right? You feed it the initial conditions, the constraints, and the prices. And by the way, we specify a range of these, and over the 100 million episodes, we randomize in between that range so that the model eventually sees all the different combinations. So for one iteration during a training cycle, it gets the initial state, so the constraints and the prices and the process state from the data itself. And then we let the model move the manipulated variables. Then we feed that to the deep learning predictor. And the deep learning predictor says what the CV, what the controlled variable predictions will be. And then we reward the DLC, whether it did good or bad. And then we do that hundreds of millions of times. This is equivalent to thousands of years of operating experience, for example, at the control board. You can see in the first scenario, it's probably not very good. In this case, it violated this controlled variable bound and it decreased the objective function. And then over hundreds of millions of trial and error scenarios, it learns to respect the constraints while increasing the objective function. I want to talk a little bit about reinforcement learning in general. Like I've been saying, it's a cutting edge type of AI, and there's several advantages, but I want to touch on one. I think it's the most important one. And it relates to what I was talking about before, where even with traditional technologies, we have you have like a prediction piece and a decision piece. Like for APC, like I said, that would be the prediction piece would be like your models you created based on step testing. And the control piece, there would be a solver that solves. Same thing with your plant-wide LP, same thing with real-time optimization. That's a huge difference between our technology and traditional solvers. So a traditional solver has no concept of the simulation or the model versus reality. It just is trying to optimize the simulation. That's all it's trying to do. So I like to use an example. If I were a solver, right, and I'm driving in my car, and I don't know what the car in front of me is going to do, if my brain were a solver, I would have some kind of underlying prediction that I'm unaware of. And that prediction would tell me the car in front of me is either going to stop or it's going to keep going. And then I would run my solver algorithm, and that would tell me to either slam on my brakes or to accelerate. It has no concept that the model might be wrong or that reality might be different. It just optimizes that prediction, that simulation. Reinforcement learning is much different. Reinforcement learning doesn't have an underlying assumption that the simulation is absolutely correct. It understands uncertainty like you or I would. So in this case, if my brain were based on learning from experience, like reinforcement learning is, then I would know from all my years of experience driving, and I wouldn't slam on the brakes and I wouldn't press the accelerator. I'd probably take my foot off the accelerator and hover over the brake, because I know that the underlying model for what might happen in the future could be wrong. I know that there's uncertainty in what's going to happen, and there's no perfect model that's going to tell me. And so I can account for that. Based on all my years of experience driving, I can account for that. And that's similar to what you get with reinforcement learning. Sometimes we tell people that it develops this human-like intuition, and this is how it does it. There's other advantages that I think are less important, but one is that it's a pre-optimized solution. So it's computationally efficient. You can run it on your existing hardware. It will always converge no matter what in a matter of seconds. You're not going to have solution flipping like you have sometimes with solvers. And then also, lastly, it can handle the complexity of the underlying predictor. So if you have a complex underlying predictor, like say you had an AI model, right, and then you put a linear solver on top of it, you're going to run into situations where you don't reach the global optimum. So that's another advantage. But again, the big thing here is that it's much less susceptible to model mismatch, and it helps the model act in a way that it can kind of have some of this human-like intuition. Similar to the deep learning predictor, for the deep learning controller, we have an interactive application. And here you can run a lot of what-if scenarios. Customers are really liking this, again, not just to evaluate our models, but to collaborate. To collaborate based on data, to have database and evidence-based collaboration. It's not like this group has their one model that's based on these types of first principles. This group has their own model based on these types of first principles. For example, like plant-wide LP, advanced process control, and your steady state model. This is one model that contains all of those things that those people care about, and it's based on your plant data. So it really helps facilitate collaboration on top of help us evaluate our models. If you would like a demo of any of this stuff, we're happy to set that up. So just let us know. So the key takeaways here for the presentation is that deep learning process control models optimize nonlinear processes, and we use it. We do that using deep reinforcement learning. More generally, data-driven AI models unlock new optimization value that maybe wasn't applicable or wasn't available before all these breakthroughs in AI. And then fitting in with traditional technologies, again, they've added a ton of value, but we have to be very careful. Traditional technologies, by definition, impose a lot of hard assumptions, and if we're not careful, they can really start to erode the value of the historical data and of AI in general. Before we go into questions, I have one last piece. We have kind of an interactive demo. We call it an optimization duel, where people can try to play with a model and see how they can optimize and see if they can actually beat the AI. A lot of our customers like to do this with various teams. So if you're interested, please scan the QR code, sign up. We're happy to set something up. With that being said, though, we'd love to move to questions and answer any questions you may have.